Well, in previous lesson, we consider basic data types. We start to discuss about basic data types in C and C++, and we discuss that the particular data type is defined by set of values, set of operations, and storage structure. The examples of data types are natural numbers, integer positive numbers, integer number, both positive and negative numbers, real numbers, positive and negative numbers with a fractional part. And for each data type, we can apply a set of operations. So each data type has a set of values, and integer numbers has some predefined range of representation. We can apply only a fixed number of operations for each data type, and the values of particular data types are stored in computer memory using some storage structure. We will discuss about the particular way of storing the numbers in computers later if we will have a time for this. Now we're I want to consider just main points related with operations and a set of values. And again, I want to repeat that except numeric data types in C++, there are some other data types like characters, yes, logical type, and so on. And we discuss that the integer type can be signed and unsigned. And for if you use just int, by default, this variable, this data type is considered as a signed integer with a sign, positive and negative. And the range of representation is from minus 2 power 31 up to 2 power 31 minus 1, approximately plus minus 2 billions. And if the type is unsigned, the range of representation is from 0 up to 2 power 32 minus 1, that equals to approximately 4 billions. We discuss about special operations that can be applied to integer numbers. These two special operations are integer division and getting the remainder. Let me briefly repeat this. The operation the division that applied to integer numbers is considered as integer division, and the operation that denoted as a person signed is considered as a remainder of integer division. I show you several examples from previous lesson. Let me run this simple project again. I enter two numbers, for example, 5 and 2, and result of the division 5 over 2 is 2, and the remainder is 1. So 5 equals to 2 times 2 plus 1. And if I enter any other number, for example, 103, the result is 33, and the remainder is 1. You can get these results if you use division, and both operands, both parameters are integers. Well, I don't want to consider some features of integer numbers. Again, we will consider it later because these features, it's very useful to understand these features, but it doesn't relate directly to your programs that you write on practice right now. Well, that's why the next data type, the next data type that I want to discuss with you today are real data types. Real data types means the data types that can store real numbers, numbers that contains not only an integer part, but a float part, fractional part too. How we write real numbers in a usual life? Can you give me an example of a real number? 2.5. 2.5. Yeah. Another example. What? 3.6. 3.6. Very good. But I would stress that sometimes in mathematics, we write a real number not in this form. 2.5. What is the meaning of this notation? 5,000. 2.5. What is the meaning of this notation? 2 is integer part. And what is the meaning of 5 after the point? It's decimal. Like how? Decimal. Yes, decimal. But how to write this number in another form? Do you know? 5 down 2. 5 down 2. 5 down 5 2. Over 3. 5 over. Sorry. 5 and down 2. 5 over 2 over 2. You can write. Okay. Yes, you're right. In this case, you're right. But for example, if I write here 2.3, what should I write? 23 multiply 10 and is power minus 1. What? Sorry. 23. 23. Multiply 10 with power minus 1. Minus 1. Right. Or 23 over 10. Right. It equals to 23 over 10, or just another form, either 2 and 3 over 10. We can write these fractional part as a fraction, 3 over 10, or 23 over 10, or any other numbers. For example, in some cases, I can write 1 over 7, right? This is also an example of a real number, but I cannot convert directly this number to this form of representation. one of such simple numbers as 1/3. How to write 1/3 in this form? What will be the value of 1/3 in the form with the point? 0.333. 0.333. Right, right. You are right. 0.333, and this sequence of 3 is endless. Endless sequence. So there is a very important fact that real numbers that can be very simple like this, that can be very simple to write as a fraction, these numbers cannot be written in a form with in decimal form. Cannot be written. More precisely, of course, it can be written, but with endless fractional part. It cannot be written with a finite decimal part, with a fixed number of digits after decimal point. Well, let me repeat this example here just as a comment. 1/3 in another notation equals to 0.33333, and this fractional part is endless. Well, some real numbers can be written in decimal form with a fixed number of digits after decimal point. For example, 1/2. Very simple example is 0.5, and that's all. But 1/3, it can be written. It can be written. Well, and again, I don't want to go into more details now, because in computer arithmetics, we should remember that all the numbers are stored in binary form, not even in decimal, but in binary form. And this problem has a more is bigger. This problem is bigger. For example, 1/2 can be represented in computer exactly, but 1/10, yes, it can be represented on pen and paper, on the paper, but it cannot be represented in computer exactly, only with some predefined accuracy. Well, but on this example, I want to show you that we store the numbers in decimal form. As far as computer has some fixed amount of memory, we cannot store this endless sequence of digits. And any type has only fixed number of digits after decimal point. The real numbers cannot be represented in computer exactly, only with some accuracy. Well, this is example what related to representation of fractions. But another example is how to represent maybe very large number. For example, 1 and many zeros, 0.5. If this number, okay, let's be just 6 zeros for simplicity. Yes, 1 and 6 zeros. 1 and 6 zeros. How I can write this number in another form?
10 by 10.
10 times 10 times 10, yes, 6 times. In mathematics, we use this notation 10 power 6. So I can write this number in a very short form, 10 power 6. 10 power 6. I just repeat 10 power 6, and this notation helps me to write very large number in a short in a short form. In a short form. And in computer arithmetic, we use some combined notation that is called scientific notation, scientific form of real numbers. Any real number is represented in the following form: m times 10 power p. Any number can be represented in this form. For example, if we consider 10 power 6, p equals to 6 and m equals to 1. This coefficient m is called mantissa, or floating point coefficient. P is called exponent part, or power. And here I write you several examples. For example, this number, I put here space, 12 thousandths, 3 hundredths, and 45. How I can write in this form? Very simple. 0.12345 times 10 power 5. But this number, I just write it here. Unfortunately, if we didn't make any other suppositions, this number can be written in different forms. For example, I can write here as 12.345. Yes, times power 3. So if we didn't make any other suppositions, this notation is not unique. And usual supposition is that mantissa must be between 1 and 10. If we made such supposition that mantissa is must be between 1 and 10, this notation becomes unique. What is the unique notation for this number if we suppose that mantissa is between 1 and 10?
1.2345 times 10 raised to the power 4.
Yes, and for all other examples, I write it here. I write it here like this and like this. And for all other examples, I can write notation, this unique notation that corresponds our supposition that mantissa is between 1 and 10. 1.2 times not -4, but -3 here. And if the number is negative, so again, there are a lot of different notations, but only one notation corresponds to our supposition that mantissa must be between 1 and 10. 1.562, 10 power 1. Well, for any number, we can write this unique notation. And in computer memory, the real numbers are stored in this form that called scientific notation. But again, here I don't want to go into other details, but of course, these examples that I write for you here are examples with decimal numbers. In computers, the situation is exactly the same, but with binary numbers. So the Mantis exponential part, all these numbers are written in binary, and Mantis is between, for example, between 1 and 2, but let's consider all the numbers as the decimals. And if we store a number in this form, the main question is what is the number of digits after decimal point in Mantis, and what is the largest power of 10? Well, when we store this number, it's enough to store just m and p. We don't need to store 10, just Mantis and power. Any real number is represented by these two values, Mantis and the power. And the particular real data type, it fully describes by means of number of digits after decimal point in Mantis, number of digits, and the power. If the number of digits is small, we can represent the number with a small precision. If the number of digits is large, we can represent the real number with high precision. And if this power is small, we can represent only relatively small numbers. If this power can be large, we can represent large numbers. Well, and when we use 4 bytes for storing the real numbers, in this case, the number of digits, decimal digits in Mantis, approximately 6 or 7, because there is no strict correspondence between binary numbers and decimal numbers. Let's consider seven significant digits. And the power is the largest power is 38. So we can represent the real numbers with Mantis with 7 digits after decimal point, and the power is 10 power 38. 10 power 38 is a rather large number, but the number of digits after decimal point is not very large, just 7. And in some cases, it's not enough to represent the real numbers with their high precision. Well, this description, this format of representation corresponds to the type float in C language. If you use float, you should remember that you will represent the real number only with 7 digits after decimal point. And there is some feature, for example, again, seven digits after decimal point, right? Remember, 1, 2, 3, 4, 5, 6, 7. This is the last digit that can be represented in float. And if you consider, for example, this number 1 plus 1.000001, what will be the result? The
1.0.
the real result in mathematics that you can find using pen and paper will be 1, 0, 0, 0, a lot of zeros and 1. But in computer arithmetics with a type float, you get 1. You get 1. So this result we get in mathematics. But in computer, 1 plus this number, the result is 1. Let's check. Let's check this very strange fact. Well, this program I comment this part of the program. Okay, let me declare two float numbers, x and y, and let x will be. Okay, let's start from the simple example. Let's x will be 1 and y will be 0. A lot of zeros and 1. And after that, let me output to the screen the result of this operation. X plus y equals to x plus y and end of line. We will see 1. Because in a type float, we can represent only 7 digits after decimal point. All other digits, they will be lost. Well, but if I write this number, y, 1 point, let's again for simplicity consider, okay, how 1, 2, 3, 4, 5, 6, for example, 9 zeros. What will be the scientific notation for this number? 0.9 zeros and 1. How to write this number in scientific form?
1 times 10 raised to power minus 9.
Minus 9, right. Maybe not minus 9, but minus 10, because 9 zeros and 1. It's a power minus 10, but you're very close. So this number, it can be represented in scientific form. Let's check it. Let me output these numbers separately. X equals to x and y equals to y. Well, we will see on the screen this notation. X equals to 1, y equals to this notation. And this form will exactly corresponds to their. Let me open this presentation again and show. Okay, this form of a real number. This form of a real number exactly corresponds to this scientific notation. This coefficient means M mantissa. This symbol E means 10, and the minus 10 is a power. So this notation, because on the screen, on this console output, we cannot use the subscripts and superscripts. The notation is as follows: 1e minus 10. This notation corresponds to m times 10 power minus 10. So the feature is that we can represent this number in computer, but when we try to add this very small number and relatively large number as 1 plus this number, we get 1. The result is 1. Because the number of digits after decimal point is 1. Oh, sorry, number of digits after decimal point is 7. Is 7. For the type float. Okay. The next type in C and C++ is double. Double have 2 times more digits in fractional part in comparison with float, and it twice more precisely represents the real numbers in comparison with the float. First, it requires 2 times more bytes for storing the number. Float requires 4 bytes. Double requires 8 bytes in computer memory, and double represents 15 or 16 digits after decimal point. Exactly. And the power of exponential part is 308 plus minus. So this is extremely large number, and in all usual calculations, it's enough for us to make the calculations with such precision. So 15 of digits after decimal point, and the power plus minus 308. So I can write here not float type with a single precision, but double. The more so-called more powerful type with a high precision. In double, the fractional part, the number of digits in a fractional part is 16 or 15. Let me write here this command. This command allows us to output to the screen 15 digits after decimal point, cout point precision. And let's see the result. We will see the real result. But if I type here more zeros, more than 15 zeros. More than 15 zeros. For example, 18 zeros, the result will be the same because this 0.00001 is outside of the range of representation of real numbers. Well, so when you work with real numbers, you should always remember that any number is represented in computer memory only with a fixed number of decimal digits after the point. For the type float, this number of digits is 7. For the type double is 15 or 16 digits, but not more than that, not more than that number of digits. Well, in some compilers supports the type long double, which uses 10 bytes for representation in computer memory. And in the type long double, the number of digits after decimal point is 19 or 20. And very, very large power. It's close to 5 thousands. But in Visual Studio, you can type long double, but actually long double equals to double. So there is no difference between these two types. Long double is supported by other compilers. Unfortunately, we cannot use long double here. Well, how to write literal real constants? This question is not so simple, like it looks at the first glance. The real number can be written in scientific form. Plus minus n point d, e, and p. Plus or minus specify the sign. N corresponds to integer part, d corresponds to fractional part, and p corresponds to power, exponential part. And the symbol e, it means 10 power p. So the result that you see on the screen, that the number, for example, a very, very small number is output to the screen in a scientific form, 1e minus 19, you can use this form in your program. You can use it here, 1e minus, for example, 10. You can use this form here in the program to write a very small or very large number. Of course, if the number is just, for example, 0.01, it's better to write in this number in the usual form, 0.01. But if the number is very large or very small, it's better to write it in scientific form, 1e minus 10. To be sure that the number of zeros after decimal point is 10, not to count the number of zeros, 1, 2, 3, 4, 5, and 10, but write 1e minus 10, and this number will be used in your program. And the same for very large numbers. 1e10. It corresponds to 10 billions. Very, very large number. Yeah, and you see that result of this addition also will be 1, 0, 0, 0, 0, 0, 0, and 1. Yes, 1 plus e. But if the power will be larger, for example, larger than 15, for example, 1e20, 1 and 20, 1e20 plus 1 will be 1e20. This 1 will be lost. The result is 1e20. So all the operations with decimal, with the real numbers, it will be performed with some accuracy, some accuracy. Okay, let's come back to the presentation. Yes, and also you can use even a short notation for the real numbers. For example, if you want to write the number 0.001, of course you can use this usual form, or for shortness you can use even this form, 0.001. You can skip for 0, and compiler understands that this is 0.001. And also, I told you on a previous lesson that this one, if you type it just as a 1, is considered as an integer 1. Let me show you the result, this result. Again, this result, because it's very important, and sometimes students made the mistakes. For example, 1/3 equals to, and output to the screen 1/3. I show you this is example on previous lesson. What will we see on the screen in this line? 1/3. Do you remember?
0.3.
0.3. No. We will see. Sorry, as I forget to write equal sign. But it doesn't matter. We will see 0. Just 0. I show you this example on previous lesson, and I show you again right now. Why? Why will we see 0? Because these two numbers, 1 and 3, will be considered by compiler as integer numbers. Integer 1 and integer 3. And when you divide one integer number over another integer number, the result will be considered as integer part of the division. 1/3, the integer part is 0. To perform the real division, I must write here not integer constants, but real constant. Well, unfortunately, I cannot increase the font in the hints that Visual Studio shows you. But if you if you type the same program in Visual Studio, and if you move your mouse here, Visual Studio outputs you the hint that these three
It's an incident.
int is int. Visual Studio considers this number as int. How to force it to consider it as a float or double? You should
3.0.
3.0. If you type 3.0,
Double.
yes, it becomes double. All the constants written with the fractional part are considered as a double constant. And if at least one argument of this operation is double, then the result of this operation will be double too. So 1 as integer over 3 as a double, the result will be double. 3.33333, and in mathematics, again, this sequence of numbers will be endless. In computer, this sequence has a finite fixed number of digits. Okay, so there you can use this point, but moreover, you can write this number as just 3 point. And this point will be the indicator that this number is a not integer, but a float or double. Again, if you move your mouse here, Visual Studio outputs you hint that this 3 is a double. Well, to represent the real numbers, you can use this very short form, short notation. Also, yes, you can use just point and fractional part. For example, you can write here 0.3. It means 1 over 0.3. Of course, it means 1 over 0.3. Well, and also you can use any notation with the exponential part. For example, I write it here 1e10 or 3 point and 3 point and fractional part. Then symbol E, pay attention that it should be no spaces between this notation. If I put here a space, it will be a mistake. The symbol E must follow immediately after the mantissa E, and also here no spaces. Okay. So 3.2323 and so on times 10 power 10. And we see this very large number. So the number y will be represented in scientific notation, but x plus y will be represented in fixed form because I put here this comment that I want to output 15 digits after decimal point. If I remove it, we will see both these numbers in scientific notation. Cout operation, it automatically select the mode for representing the number. If this power is large, it selects the scientific form. If this power is small, for example, just 3, I can write this number with the power 3. It will output this number in our usual form with a fractional part without scientific notation. Okay. Well, during their first lessons on practice, you usually work with their numeric data type. But I want to say that there is also a symbolic type, char, that can be used to represent characters. But how to represent characters in computer memory? The characters are represented in so-called in the form of a table. The first column of this table is a code of the symbol, and the second column will correspond to the symbol. And when we consider the character, the type char, the values of the type char can be considered as a very small integer numbers, and at the same time as a characters. Integer number, the code of the symbol, and when we apply some operations, arithmetic operations, these operations will be performed with the code. And if we apply input-output operations, these operations will be performed with the symbols. The usual table contains 256 different symbols. This table of symbols includes Roman letters, lowercase, uppercase, all the symbols from the keyboard, and some part of symbols that related to some national alphabet. For example, Cyrillic symbols in Russia, or some special symbols for German alphabet or for French alphabet, and so on. Well, let me show you some example with the characters. Char A. So yes. A is a character. A is a character. But character without any value. To assign a value, we should assign the value in single quotes. Something written inside a single quotes will be considered as a symbol. So I can assign to A something written in a single quotes. For example, A equals to S. Now the variable A has a value S. The symbol S is written to A. Let's check it. Out A equals to A. We will see S on the screen. But I also told you that each symbol has a code. And this code is just an integer number. Let's output the code to the screen. It's very simple to do. I force the output statement to consider a is integer. Here, a is considered as a char, as a character, and here as integer. And we see that the code of S is 115. All the symbols are written in alphabetic order. What is the next symbol in the alphabet after S? T. Okay, the next symbol is T. Let me show you this feature. A plus 1.
Yes. See.
Right. We will see on the screen, or of course, it should be doing like this. A equals to A plus 1. And after that, we will see T on the screen. Because all the symbols are written one after another in this code table, and the codes follows one after another. For example, if I assign, for example, capital A, the code of, so A plus 1 will be capital B. Also, let's show me. I copy this to the screen. So first I output to the screen. After that I add 1, and after that output again. Now I assign to a symbol 0. All the symbols are written one after another. 0, 1, 2, 3, 4, 5, up to 9. So a plus 1 now will be 1. The code of 0 is 48. So when I add a plus 1, we will see 1 and the code 49. I can put here plus 10. Or 10 is not a good example because it will be outside of digits. We have only 10 digits. Okay, plus 7, maybe. Plus 7. And we will see 7 on the screen with the code 55. The same operation I can apply for any other digit. For example, not digit, but simple, D. A equals to B. And D plus 7 will be K. With the code 100. So again, when we discuss about representation of the symbols in computer, you can imagine that all the symbols are written in the form of this table code and symbol. Here, let me, for example, what is the code of A? Of course, I don't remember, but it's very simple to to find. What is the code of A? The code of A is 97. For example, the code 97, code 97, and symbol A. Code 98, symbol B. Code 99, symbol C, and so on. So all the symbols are stored in such a table. And when you output the symbol to the screen, you see the symbol. So when you output to the screen the variable of the type char, but if you apply some operation with the variable of the type char, this operation will be applied to code of the symbol. Let me come back to Visual Studio. For example, A equals to B, and I can apply subtraction, D minus 1, and we will see on the screen the previous character, A, B, C, D, E. So we will see on the screen C with the code 99. Well, and also there are some, maybe the last feature that I want to show you this on this lesson, that in C language there are some symbols, so-called unprintable symbols, symbols that can be output using a special command. And maybe the most useful example for you will be the symbol that corresponds to enter a new line. And this symbol in a program is represented as a /n. When I can assign this symbol to A, even like this. It's /n is one symbol, or it's better not to assign, but just output this symbol to the screen. If I type it here, /n, it will be considered as a new line. You see that here new line starts. And all other symbols, for example, /t corresponds to tab. Not a space, but a tab. And we will see tabulation tab on the screen. And so on. There are a lot of symbols. For example, how to output the quarters to the screen. Because if I try to type here quarter, this quarter will be considered as the end of the string that I want to output to the screen. And to output the quarter to the screen, I should use this symbol /quarter. Now the word quart will be in quarters. Well, okay, it's more or less to say that that's all that I want to consider with you for basic data types in C language. We consider maybe the most useful properties, the most features of this data type that will be useful for you on practice. We consider the integer data types, we consider float, we consider real data types, float and double. We consider character data type char. Next lesson, we will discuss about operations with data types. Of course, some operations we already consider. Some simple operations like addition, subtraction, multiplication, it's very simple. But there are more complex operations that also are useful. And we will consider these operations that can be applied for these data types next lesson. That's all. Do you have any questions? Maybe students who connect to our lesson in Teams. Any questions?
I have a question. And The initial example that the initial I think I can't remember the name, but you know the representation like this. You said like when you do calculation in mathematics, like 1 plus 0.00001. In mathematics, it will give you 1.0001.
Yes.
But on the computer, it just give you 1.
Yes.
But you run a program now, I think, like the second to last one you did now, but it wrote out the complete digits, 1.00001.
Well, the result will be 1 if the number of digits after decimal point will be larger than the number of digits that can be represented in this data type. Again, if you write here, for example, 1e minus 3, let's output here with the precision 15. No, let's write it here. Okay. Well, if you add 1 and 1.001, of course, the result will be precise. But if this power will be smaller than the smallest possible power, the result will be wrong. It will be correct in computer. It will be wrong from the point of view of mathematics. In mathematics, if you add two different numbers, you cannot get the same result. 1 plus small number, it cannot be equals to 1. But in computer, when you add 1 plus small number, you can get 1 if this number is very small. Well, more questions? Well, if no, I stop sharing my screen and I stop recording.